All right, so for this one, I'm going to go over pH 79. I'm really just going to focus on either the Vesper or IMA. So I'm going to ignore the other stuff that are kind of review just to make this video a little bit shorter. So on the first one, it is sketch a molecule of 1-propanol. And the other one is going to be an ether. All right, so 1-propanol, when you look at it, you should have memorized, excuse me, my dog, you should have memorized propane. So this is the root word, if I spell it correctly, propane. So this is a hydrocarbon, prop is 3, and then you have 1, 2, 3, and then it is saturated because of A, so that means you're going to have an H on every one. So this is propane, but we don't have propane, we have propanol. So this right here tells me I'm going to have an alcohol added to it, alcohol. And this alcohol is going to be somewhere. The alcohol is a OH substituent or, substituent. And what it's going to do is it's going to be somewhere. It could be on any of the C's, but here it tells me it's going to be on the 1. So it doesn't matter which way you count, left to right or right to left. 1's going to be here or 1's going to be here. Even if you pick this one as 1, it is totally fine because when you flip it, rotate it 180 degrees, it's the exact same thing if I did on the other one. So here is 1-propanol. An ether of this, and it says is an isomer. So that means isomer means it's the same structure, but now it's going to be in a different order. And ether just means you have oxygen in between 2 carbons. It doesn't matter what kind of carbon it is. So we're going to, okay, well, I'm going to put it right here. So I have a C, C, I'm going to put an O right there, and then another C. And now I'm going to try to fill in as many as I can. So carbon needs to be bonded into 1, 2, 3 things. 1, 2, 3, 4, 5. So here it is. Oxygen has 2 lone pairs, so it should look like that. H, 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 H. All right. So here are my structures, Lewis structure. So these are not 3-dimensional. I just want to make sure I have the right number of each one. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I have the same number of H's, same number of C's, and 1 O. So these are isomers of each other. They have the same chemical formula, but they have different structural formulas or structures. And then what it's going to ask for, we're not going to worry about the Vesper for this because this is kind of complicated. It's much easier to do it on a molecule model that we see because these bonds, you'll learn later, they can rotate. So there's multiple ways you could kind of draw it and you'll be totally correct. But what we could do though is figure out whether something is polar or non-polar. Okay, so here we have a couple things. You have something that's very polar or electronegative. And both of these and what's going to happen is they're going to pull. So you do know that oxygen is a bent shape. So even though I'm going to ignore all this, so this is a blob and here's a blob. Since it's a bent shape and not a linear shape, what we could do is talk about what's going on. So oxygen is more electronegative than carbon, so it's going to have a net dipole that way. Here's another carbon, it's going to net dipole that way. So overall, the net is going to be up. So here we're going to have a polar item. Here we have the same thing. So here is my oxygen. Here's the carbon chain. And like I said, it's a blob and we're going to ignore it. And here's a hydrogen. And it's also going to have a net dipole this way and a net dipole this way. So it's going to have a net polar. The difference between the two is that here you're between 2 carbons. So even though it's polar, it's only dipole, dipole, dipole. Here, even though it's still polar, but here you have a special case because you have hydrogen. So whenever you have oxygen and hydrogen, nitrogen and hydrogen, or fluorine and hydrogen, you're going to have a stronger dipole, and a special case of it is called a hydrogen bond. So this is a dipole as well. But since you have a hydrogen, it's a special one, stronger. You have something called a hydrogen bond. So I kind of like you to know what alcohol is, I like you to know what an ether is, and you should know the first three. You should know methane, you should know ethane, and you should know propane. Oops. And really you should know butane as well. So these are all natural gases, fuels that we use. So at home we use methane. Most likely you're going to use propane or butane in some sort of container that cooks something. And then ethanol is something that we put in gasoline. So these are really common, and so I just like you to know it. Like, I'm not going to make you know anything above decane, but at least know the first four. All right, so that's that one. So we sketched the molecule, we did the Lewis structure, we talked about IMF, intermolecular forces, and then which force it is. So dipole, hydrogen bond, and then this one is just dipole. All right, number 2. This one you have C2H4, and then you have C2H4F2. So you do want to do the Lewis structure of this. After a while, you don't have to use SNA. And this one, SNA doesn't really, I mean, it does help, but you have to do it for both carbons. But after a while, you just know, okay, carbon's going to bond with each other. Hydrogen can only bond with one thing, so it won't bond with hydrogen because then it'll be H2. So here, we're just going to start adding. H, so that's 1. H, that's 4. So now we have 4, so that means, remember, carbon wants to have one more bond because it has one more lone pair out there, or lone electron. So what you're going to do is make something called a double bond. So this is what you have. Now this is a Lewis structure. In reality, it looks like this. If we just focus on one of the carbons, it's bonded to 1, 2, 3. It has 3 things attached to it, so that means it's going to be a trigonal planar. So the correct way of drawing this will be like this. So this is a trigonal planar carbon and another trigonal planar carbon right here. And that is going to be your shape. And then the bond angles between the adjacent H's right here is going to be the same as a trigonal planar, which is 120. So remember, this carbon has 3 things around it. And because it has 3 things around it, it's going to be trigonal planar. Okay, this one. If I draw it out, carbon is going to be bonded with carbon, and then you have your 2 hydrogens, and then you have your 2 fluorines. This carbon right here has 4 things attached to it. So what's going to happen is if it has 4 things attached to it, it's going to be a tetrahedral. Oh, what is going on here? Whoa. Sorry. I don't know what's wrong with my computer, but that's tetrahedral. Maybe I was talking too or writing too fast. And now the bond angle between these, each one is going to be 109.5 degrees. So 4 things tetrahedral, 3 things trigonal planar, 2 things is going to be bent. So that's all we know right now. There are special cases, or no, did I say 2 things bent? 2 things is linear, sorry. There are special cases with tetrahedrals. There's the pyramidal, which is 1 lone pair, and then a bent, which is 2 lone pairs. But right here, we just have 3 and 4, so 109.5, and this one is 120. So that should be number 2. Let me make sure. Oh, we want to do intermolecular forces. Here, we have carbon, hydrogen, and even though carbon is more electronegative, it kind of cancels out because you have it pulling equally from both sides, so not much. This one, I'll be honest, I am not going to give you a molecule like this on your mini exam tomorrow just because we never talked about more than 1 carbon chain. So this one, I'm just going to leave blank. I'm not going to add something so complicated, but if it was just C, H, F, H, then this would be a dipole. So if we just not had this extra one and just had 1 central atom, this one is going to be a dipole because the fluorine is more electronegative. So this part is going to be partial negative, and this one's going to be partial positive. So the only time I'll give you something more like that has a bunch of carbons to it, it won't be symmetrical. This one's symmetrical, so it's kind of tricky, but I will give you one that's not like what we had before, which is propanol. So this one is a hydrogen bond. All right, so just don't worry about this. I'm not going to give you a symmetrical one like this, but if anything, it will be something like this. All right, so the next one will be number 3. Get rid of this. You have CCl2F2, and then you have SO2. All right, so CCl2F2, C is going to be in the middle because both of these, if you draw it out, this has 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, and then fluorine, same thing, 1, 2, 3, 4, 5, 6, 7. So these only could do 1 bond each. Chlorine, carbon could do 4, so most likely it's going to look like this. And since it's symmetrical, meaning fluorine is going to pull in the opposite direction, chlorine is going to pull in the opposite direction. This one most likely is just going to be a tetrahedral because it has 4 things around it, tetrahedral. So that's 109.5. And if I ask for an IMA, this one will probably just be London dispersion. Okay. SO2, this one has 1, 2, 3, 4, 5, 6, I believe. Yep. 1, 2, 3, 4, 5, 6. So when you do SNO, you have 3 things that want to be noble gases, so that's 24. Each of them has 6, so 6 times 3 is 18. So we're going to share 6 electrons or 3 bonds. So you have here is your what's it called? Your Lewis structure. If we're going to focus on the central atom right here, the sulfur has 1, 2, 3 things. So since it has 3, it is going to be a trigonal planar. But in this case, you only see 2, so we call it bent, just like our water. So our water has 2 lone pairs, and we still call it bent. So it's bent. So it's going to be about... Oh, this has 2 lone pairs. Sorry. What? Did I get that right? 3, 2... See, 3 times 8 is 28. They all have 6. Yeah, 6. 6. Oh, 3 bonds. Yeah, that's right. So we're going to have bent. So it's going to be about 104.5. All right. No, this one's going to be 120. Yeah, sorry, because there's 3 things. 1, 2, 3. All right. The last one is 1 pentane, and you have diethyl ether. So remember, this is pentane. So pentane is going to be 5. 1, 2, 3, 4, 5. And on one of them, you're going to have ein, so that's a triple bond. 1, 2, 3. And make sure it's on the 1. So in that case, it's going to look like this. Okay. And then here you do not have any polar or very electronegative. So we're going to say this is London dispersion. Diethyl ether. Diethyl means 2 ethanes. That's an ether, so that means an O with a carbon. And each of these carbons are going to be 2 carbons because it's ethane. And we're going to hydrate it with hydrogen. So this is what's going to look like. This one is polar because oxygen is more electronegative, so it's going to pull towards it. So the net dipole is going to be up. So this one will be partial negative, this will be partial positive, and then dipole, dipole. No hydrogen. All right. So that should be all of it. I want to go back just because I know I kind of mentally made a mistake. Here's SO. Since it only has 1 lone pair, we're going to think of it as 1, 2, 3 things. So that's a trigonal planar. So that means these 2 are going to be 120 degrees. We just don't see this, so you just draw it kind of like this. So kind of like water, but instead of having 2 lone pairs up there, you only have 1 lone pair. So if I had 2, it'll push it down even more, but with 1, it's just 120. So trigonal planar that way. Oop, forgot the lone pairs. So 120 between those 2, and I don't think it asks for, yeah, it doesn't ask for intermolecular forces. So that is pH 79.